Welcome everyone. We're going to wait just a moment for all attendees to join. We'll get started here very shortly. Okay, it looks like most everyone has joined. A few still trickling in here. So why don't we go ahead and start? So welcome to the fourth session of our Whole Tomato Summer CodeFest C++ Coding Camp. My name is Ben. I'm the Chief of Staff for Whole Tomato. And we've had 3 excellent webinars so far, covering some interesting things like concurrency, hexagonal architecture, and modern 3D. And we'll get to today's topic and presenter in just a moment. A couple of quick notes. We will have time for Q&A at the end of the presentation, so please ask questions throughout the presentation and we'll circle back to them. There are no stupid questions. I like to say if you're wondering about it, someone else probably is as well. So go ahead and ask it. We'll answer as many questions as we have time for. We will be moving through these slides quickly, so if you miss something or want to refer back to something, the slides are available as a virtual handout. You should see that as a link in the GoToWebinars handouts panel. And if you're wanting to see our other upcoming summer CodeFest sessions and topics, you can see the schedule on our site, wholetomato.com. We have 2 more after this one. And these webinars are recorded and they are available for rewatch on YouTube. So if you want to revisit them, you can just search YouTube for Whole Tomato and you should find our channel. All right, for today's webinar, we have our own David Millington, who will be covering lambdas, and he's titled this presentation, Lambdas Go By. So cue up your sheep puns, I guess. David is originally from Australia, but currently resides in Estonia. He's our product manager for C++ Builder with the Embarcadero product line, and also the product manager for Visual Assist. And he told me he began programming BASIC on an 80s era BBC microcomputer and then moved on to other languages like Turbo Pascal, Delphi, JavaScript, PHP, Java, and eventually, of course, C++. So he's a well-rounded programmer. Today, David works very closely with our own development teams, helping to manage our C++ products. And he's a strong advocate for the user community. He's very much in tune with the needs and challenges that developers face. So trust that you're in good hands with David. Beyond just programming, David enjoys writing prose, not code. He's a contributing author to a magazine that's known internationally. He's also an avid reader and enjoys cycling through the amazing Estonia countryside. Now, before we pass it over to David, I wanted to mention again that the Summer CodeFest is sponsored by Whole Tomato, which publishes the widely popular programming tool Visual Assist. I'm sure some of you may be using it, but if not, we want to give you an opportunity to check it out and learn a little bit more about it. So here, I'd like to ask our Whole Tomato lead developer, Chris Gardner, to tell you a bit more about Visual Assist and how it can help you with your C++ development. Chris?
Hey everyone, next slide please, David. So Visual Assist is a plugin for Visual Studio 2022 and lower, and previous versions, of course. It's a productivity tool. Many features. Think of it as IntelliSense on steroids. It has all the basics you'd expect to find references and finding symbols, and we do it in such a way that you're able to very quickly and easily and powerfully move around your solution, regardless if it's a gigantic solution, if you're programming in C++ or C#, if you're working in Unreal or Unity, or your own custom engine. It's a very powerful tool. It's a popular tool that's helped a lot of developers. Next slide, please. So we're mostly known for navigation, refactoring, code generation, etc. We have many features as far as debugging. The list goes on and on. There's so much I could say about Visual Assist, but the most important thing I would say is you should probably just try it for yourself if you haven't. So if you go to our website, you can go to wholetomato.com and you can download a free 30-day trial. That I think is the best way to see for yourself if this is a tool that's going to be helpful to you. And one tip that I would share is try using Shift-Alt-Q. Once you install it, use Shift-Alt-Q, and that's an easy way to access many of our refactoring tasks right from the keyboard. And that's basically what I wanted to say. So we'll start with the webinar now. David, over to you.
Thanks. Well, thanks, Chris, and thanks, Ben. So today it's all going to be about lambdas, and we're going to go through a few things. First of all, just why a talk on lambdas. They've been around for a bit over a decade. So why a talk now? We'll quickly skip over sheep. It's really just a bad pun. We'll look at comparing lambdas to functors, which are an older C++ technique. How lambdas work as an alternative, and then a whole bunch of sort of interesting things and a summary. And so the first is why to give a talk on lambdas. Now, here at Visual Assist, we see a lot of C++ code from a lot of people, and there are a lot of people who heavily use lambdas. And I put those in the love lambdas camp, as in, of course I use lambdas. Why on earth would we have this webinar? And then there are a lot of people who don't use lambdas at all, and they tend to use functors, which I'll also cover, but you may be familiar with since they're predate lambdas. So I call them the favor functors camp, and of course they do the job perfectly well. So why this webinar? And really lambdas I think are a beautiful construct, but there's quite a genuine, perfectly valid feeling that other ways are fine, and that's true. And I'm actually not going to try to tell you in this webinar that any other ways aren't fine. I just want to try and tell you in this webinar that I really like lambdas, and hopefully sort of convince you of that a little as well. And as level of like the height of my sense of humor, I found like lamb and lambdas a pun that tells you everything you need to know. I actually grew up on a sheep farm in Australia, and when I was about 7 years old, I had a pet lamb that looks just like the one in the photo. So I thought I'd throw in a few sort of sheep facts from my time growing up on a sheep farm. They're actually very intelligent. I think people have this kind of stereotype of sheep as dumb creatures, perhaps because they're herd animals, and of course, people refer to others, unfortunately, as sheep, as saying something not very nice. But they're actually very smart creatures. The only main problem they have is they can get trapped if they lie down with their feet uphill, and then you have to go and rescue them. And something that I actually didn't know until a couple of days ago was that the ancient Egyptians mummified sheep's heads. There have been at least 1,000 sheep's heads found, most of which were apparently given as some kind of sacrifice or homage to Ramses II 1,000 years after he died. So how about that? I found that rather unusual. But this is actually a C++ talk, so let's leave lambs and go on to lambdas. So I want to talk about C++ function objects. And a lot of talks sort of go into sort of what they are and how to use them, but I want to approach this with a sort of problem, like a reason that you use this kind of technique, or a problem that this kind of technique answers. And that problem is that you want to run a bit of code on something, that's normal, but the location of where that code should run is inside something else that you don't necessarily write, library code, for example. It's not directly there in the method that you're writing right now. It's somewhere else. It's injected. An example would be sorting. Now, when you're sorting things, you need to have a comparison function. A is less than b or not. But the actual sorting code, the algorithm, has probably been written by someone else. So the sort code isn't yours, but the actual comparison for your objects is your code. Or searching is very similar. There are lots of optimized search algorithms out there. You're probably using a standard search library, but the actual logic for matching something is probably written by you. So you have code that's yours, then you call into code that's not, but you want the code that's not to run code that is yours. Threads are another example. The actual work of running a thread is not something that you normally want to deal with. Some library does that. You probably use std thread. But the job that the thread needs to do is yours, and so forth. This is a really common pattern, and it's a code layering problem where your logic goes in something else. Your code calls into other code, which needs to call back into your code. Now, there are many ways to handle this kind of problem. It's a very standard kind of design issue that is faced in many languages and apps. You might pass around interfaces, and so you know, some code might expect an interface, and you pass it a class that implements that, and then the other code will call into those methods, for example. But you know, going by C++ for small discrete bits of code, the ideal construct is a method, you know, a function, because that is a small discrete bit of code. In the really old days in C, you would have sent in a function pointer. In C++, you would send in a function object. So you have your code that calls into something and runs your code again, and the bit that you send in is a function or a function object. So that's where we've got to. We need a function object, and that's where operator bracket bracket, the call operator, comes in. Now anything that can have operator bracket bracket, operator call, called is a function, and a struct or class or whatever that has that operator is a function object. So on screen you can see a struct called foo. It has operator bracket int I, and then that's a method that does something. But because it has the operator, the call operator, operator bracket bracket, you can see that you can have the struct itself, an instance of the struct called f, and directly call it as though it was a method. And effectively it is, it's a function object. So that's a super brief overview of a problem and a solution. Now the old way to do this in C++ was with a struct with the call operator. So suppose I needed some kind of comparison, let's say in a sort or something like that. I might define a little method that compares my types. Here I've used integers, but that's just to have very short code on the screen. And then I put that in a call operator and put that in a struct. And then in my sort code, I would pass an instance of my struct, which has the call operator into the sort method. Now that's called creating and using a functor. So the struct that has the call operator is a functor, which is a type of function object. So std sort, and we're just using this as an example, expects any function object that can take two integers when it's a vector of integers, say two of whatever the type is, and returns a boolean for if one is less than the other. And the key to get here is that when sorting, it calls the function that you send in. So I'm just returning here to how you pass in a function or a function object. And in the code that I had on the previous slide, I had passed in an instance of my comparison struct being created, and using, again, slightly older syntax, I created that with 2 brackets. I've seen a lot of code bases that actually found that confusing, because what you're passing in is a function object, and people created those using the same braces, and so that was therefore confusing. So it would often be created just on the previous line and then the instance passed in, as you can see on the screen. Both the lines are equivalent, but effectively what you're doing is you're creating a little structure, a little object, which has this operator, and passing it in. Because it's a function, it can be called. So this looks quite a neat solution. You can write a little structure that has some logic and pass it around somewhere, just like any other variable. I mean, it's sort of ideal for passing into a method and using to inject into some other code that needs to run something. So what's wrong with doing that? Well, not much, to be honest. It does the job. And more familiar with structs, and defining operators is a fairly basic C++ thing. The call operator is just another one. So far so good. However, it is a lot of extra code for a small job. We're writing an entire structure where really you just want a single method, and that's because you can't really easily represent just the single method, especially if you need to capture state. And to me, this is the biggest thing as well. It's usually defined off screen from where it's used. So in the code you can see on screen, I have my struct and my operator, and then a ... and then later where I'm using that functor. Now that ... can represent a lot of code. It's probably a page of scrolling at least. You might not even have it defined in the same same file. And that means that the code that's actually being run, which is often quite short, is not visible on the screen at the point that you actually inject it. And seeing code is useful. And I know this seems kind of obvious in a sense, because of course seeing code is useful, but it really is useful to be able to write some code and see what's executed in line with the code that you write. And with a functor, you often can't do that. It's usually in most code bases defined somewhere else. And you have to go and look it up if you actually want to see what's being run. So with that, onto lambdas. Now, a lambda is also a function object, but it's defined with smaller syntax. And it's almost always written directly in line. And on the rare cases it's not, it's almost always defined very close to where it's used. And there's another 1% where it's defined somewhere else, but usually written in line, or at least so the code is visible. And they're more powerful and more flexible than functors. So here's an example, just a comparison of the two. So on the left is a standard functor, like I wrote before, and on the right is the lambda equivalent. And you can see the lambda is a lot shorter. So with the functor, I have to write an entire struct with my operator, whereas on the right, I basically just define a method inline. And after all, that's the point. I just want to pass in a function, and Lambda syntax allows you to just write a function right there in line where it's going to be used. And I prefer the code on the right, not just because it's shorter, although concise code is good, but because I can see in my bit of code that's calling std sort here, I can see exactly the code that is going to be called right there in line in the place that it's used. And I think that in general, seeing the code that is run in line where it's used is better in terms of code understanding than referring to something else. I know all code ends up referring to other things, but especially for small bits of logic, it's good to have them visible. So much shorter, much more visible. We're passing in a function. I think more readable because it is shorter and more visible. And returning to the same diagram, instead of passing in a functor, we're just, which is a type of function object, we're passing in a lambda, which is another function object. So lambdas are concise, visible and readable, and powerful and flexible, and they're just another way to define a function object, the same as a functor, but in my personal opinion, better. And really, that's it. And I could end the webinar here, except there's a whole lot more to go into. But that's kind of the pitch for why lambdas are so good. So let's dig in a bit more into the syntax, because I mentioned that you're writing a function inline, and you may have recognized that there were the curved braces as you normally get for a method, and the curly braces as you normally get for the body of a method, but there was another set of braces as well. So lambda syntax is basically 3 sets of different brackets in front of each other, and bracket, 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 bracket. The square brackets capture state. We'll get to that soon. The curved brackets, braces, say that it's a function, as all methods do. And then, of course, the curly braces say that, hey, the function actually has to do something. The same as any other method. So you can see that you are actually defining a method in line, just with very concise syntax. So the bit that I ignored on the previous slide about capturing state with the square brackets. So when I was talking about functors, I showed a very simple one where the operator just was, the call operator was just called with 2 integers to compare them and returning a value. But often the logic that you want to pass around is slightly more than just a standalone method. It wants to capture some state or have some knowledge or something like that, some kind of context. And so with a functor, which was a struct, what you would do is you would give it a constructor and you would pass in some state, and it would store that in some private fields. And then, after you had created your function object, your struct, and initialized it as part of that construction, you would then pass it in somewhere, and the method operator, the call operator, would be called, but it would be able to access the data that had been initialized with which it stored, like any struct in its own fields. So you might wonder how to do that if you're writing just a method, because of course the value of a struct is that it can store data. So how does a method do that? Well, lambdas do that through capture, and they achieve exactly the same thing really, but writing a bit less code. So on screen on the bottom half of the slide, I have a few bits of variables that you might want your method to be able to know about, an integer, some kind of context, the string, and you can write in the square brackets the basically the data that you want your Lambda to be able to access or to know about. And this means that data that is visible outside the Lambda is captured and is therefore accessible from inside the Lambda. And this achieves the same goal as initializing your functor struct with some state. So hopefully with this, you're converted. Lambdas are just function objects. You see your code to the point you call it. They're concise and flexible. There are a few things that can be looked into. Look, variable capture I went over very, very swiftly, and it's quite powerful. So you can capture variables by value or by reference. And reference, of course, can be very handy if you want to write back to the variable. There are some shortcuts, so you can capture this to give you access to the current class instance, the current object. And there are also shortcuts such as ampersand to capture everything by reference and equals to capture everything by value. Now look, personally, I would caution against using these because when you capture everything, you don't really know what you're capturing, or rather, it's kind of imprecise. And things that you don't use won't actually be captured, but it's still a lot clearer to be explicit and to say that your function needs to know about a particular bit of data and know a particular bit of state. So I do actually recommend, although shortcuts are nice, not using them and actually capturing everything that you need explicitly and clearly. There are other things you can do, such as you can rename things. So at the bottom you can see I have an integer called I, and I want my Lambda to know about that. But within my Lambda, I'm going to call it something else. So in the square brackets, I'm capturing it by reference, auto, because compiler knows the type. The reference symbol meaning to capture by reference, J is the name, and then I say that actually refers to the integer I. And in the Lambda body, when I go J++, it actually increments I, because of course J is a reference to I. And I think that having different names like that is quite useful as well. Now, function objects, I kind of skipped over this, but it was perhaps clear in that you could pass things like functors into a method. A function object, as a struct, is something that can be assigned to a variable, and a Lambda is no different. You can assign a Lambda to a variable. So I have some code on screen here, auto f equals, and then a Lambda, can be a Lambda of any complexity. And this is where the object part of function objects comes in, because they are assignable to variables. They are objects or structs, and you can do all the things with them that you would normally expect for any other variable. There's one interesting thing is that you can often define the function signature if you use std function or something like that, but it is possible with some Lambda syntax to actually not be able to explicitly define what the type of the variable that represents the Lambda is. And in that case, you just have to use auto. You probably use it anyway because it's a lot simpler. I tend to find that when you try to write out a std function type for a lambda, you're effectively defining the signature twice, and there's no reason to do that. Signature is defined as part of the lambda itself, so you might as well just use auto. But of course, you can use std function. Now, std function can represent any callable object at all, not just functors and lambdas, but anything that can be called. Now, here are a couple of examples on screen. And you can see that, and I'm just expressing my personal opinion here, but when you write std function, bracket int, bracket, bracket, f equals, and then a lambda, look, it's far more complex than just writing auto f equals. And so my question is, why write it? You're sort of repeating something. What you wrote on the left-hand side is captured on the right-hand side, and the only reason to do it is if you actually explicitly need a std function. Also, interestingly, assigning to a std function can add a little bit of overhead, probably extremely minimal, but it is there. However, if you need a std function, such as if you want to use std bind or related capability, then you can do it. Another sort of useful example of a lambda, look, I spoke before about things like sorting and searching, but really anything where you want to pass in a bit of code that runs, and it's usually run on something. You might have a call operator that takes no parameters, but usually you'll want to pass in something to run your method on. But there are many ways and places you can do that. And actually, Chris, who spoke for a couple of slides earlier, our lead developer, gave a really good talk a few days ago about multi-threading and asynchronous programming. And he showed how you can run a thread with a lambda. So you might be used to running threads and having the actual thread execute function somewhere else. It's a great example of a lambda that if you just want to spin up a thread that does something simple, just write it in line. And that has all the benefits of being able to see your code right there. And the way to write it in line is, of course, using a lambda. So there we are. That's the summary of the various benefits as well. They're readable in line. I've gone over this quite a bit, but this is really, I think, one of the most important things about them. You see your code that is run somewhere. You see that code in the same place where you define what uses it. And for me, this kind of coherence of the location of code to where you specify that's going to be used really helps understanding code. That can be your own code that you wrote 6 months ago, but someone else's code as well. They're concise, more so than functors, which I think is useful. And they're a good way to pass around small, discrete chunks of work. In other words, to pass around methods. Not the only way, but a good way. And some things that are worth looking into, because this was a sort of brief overview, really. Look into the type of lambdas and just using auto. Capture is very powerful. And since they've introduced in C++11, there have been a number of tweaks. For example, the thing that I spoke about a couple of slides ago about renaming, or rather having a reference to a variable by a different name within the scope of the lambda, I think was introduced in C++14. Not completely certain, but they have been tweaked and improved ever since they were first introduced in C++11. So very powerful and always improving. Alrighty, so that was Lambdas Go Bar, like hopefully a fairly brief and I hope enthusiastic overview of lambdas. And I hope I've successfully sold you on why they're so useful and so cool. So we have a live Q&A now. Chris, who spoke earlier, and I are online to answer questions, and Ben, I believe, is emceeing. So I will hand over there, please.
Excellent webinar, David, by the way. That was very informative and well structured.
Thank you.
All right, well, let's dive into some questions here. We have a few coming in. Please, everyone, feel free to submit your questions at this point. So someone's asking about performance. Can you talk about performance of lambdas, like lambda versus a functor? Which one of them is faster?
Yeah, that's an excellent question. Lambdas are just as performant as a functor. So there are no performance hits that I know of at all for using lambdas. And the reason for that is that they get compiled down quite efficiently, just being effectively a function and a bit of a state. And what I think is, now I'm not a compiler engineer, but I work with compiler engineers, and so I hope I'm not misrepresenting this. But what I recall being told is that Clang, for example, actually compiles a lambda down to an internal representation that is very like a struct with a call operator. It's very close to, if not identical to, the same thing. It's just a more succinct and concise, an accurate and more powerful way of representing, the same concept. So definitely just as performant.
Awesome. What are the best practices on using lambdas with move semantics?
Well, that's a good question. And actually, I might need a bit more context on why it's asked. Chris, I actually recall that you were using move semantics in your example webinar a few days ago. Don't want to put you on the spot, but is that a correct memory? And do you want to speak about why you did that, perhaps? I think you were. Maybe you were using stdref.
Just realized I was muted. Sorry, guys. Yeah, you could use move semantics on lambdas if you need to use move. Like if you need to move something that you can't have multiple representations of, like an unshared future or something like that. I don't think I did that in my webinar, and I'd be kind of. It's certainly possible. That's the main answer. There's no problem with doing that that I know of. You just std move during the capture, and you can hand it right to the lambda.
Yeah, I mean, a lambda is there to capture context that it needs to know about. And as Chris said, if you need to move that in rather than you have a copy or something, that's completely valid. The lifetime of the lambda follows normal scope rules as well. So if you define a lambda in line in a method call, then you can expect by the next line of code after that method call that the lambda will have destructed.
All right, here's I think what is being asked, is there a limit to lambda or function size? Are there any drawbacks? Are they mostly used as a bool? Do lambdas work on MFC? So quite a few questions in that one question.
Look, there's no limit on size at all, because you're basically defining a method, and it can take any number of parameters, and it can capture any number of variables or state, and it can be as long as you want. That said, they're usually used and passed around in lines. So if you start having a really, really large one, I would at that point start thinking, is lambda really the best way to capture that? Or can its logic be divided up somehow, or something like that? Because in general, gigantic methods aren't particularly good. So that answered the size. Ben, I think there were a couple of other questions there, and I'm sorry I forgot what the other two were.
Oh, yeah, that's fine. Are they mostly used, or maybe you could speak to their drawbacks if you know of any drawbacks?
Look, I don't know of any drawbacks.
Okay, great.
I mean, look, they can be used for a lot more than just returning bool. I used sorting, for example, as an example, because it's such a small, succinct method normally. You invoke the less than operator, and that made it good for slides where you just want to have a really short method. Lambdas can obviously be more complex and do a lot more, and they might return something, some really complex type or a tuple of things or anything like that. I mean, it really just depends on what calls them, and what you want to pass into the lambda, and what you want to get from the lambda. You might write some complex algorithms over your own data types that need some kind of complex return, and there's no reason a lambda can't return that.
And then the other part of the question was, do lambdas work on MFC?
Actually, a long time since I've used MFC, so I'm not certain I can answer. Chris, I don't suppose you would.
I'm not sure either. Sorry.
Okay, we can circle back to that one later. Can you go over how you would receive how you receive a lambda in another function signature? Like, what would the syntax be for that?
Well, I would tend just to use auto everywhere I can. But really, you want to probably use std function for something that you want to describe a specific type. And then any function object that matches that particular function type will be able to be accepted, whether that's lambda or a functor or something else.
Okay. And then someone asked, I think you may have spoken to this a little bit with performance, but aren't lambdas rewritten to structs? So what about the overhead in terms of compile time, runtime?
Right. So yes, when that person refers to lambdas being rewritten to structs, I don't know if it's in the C++ spec that they must be rewritten to structs or not, but I am 99% certain that yes, you're completely correct. They are rewritten to structs, at least in Clang, and it certainly makes sense as an implementation option. So at runtime, I know of no performance impact at all. At compile time, as far as I know, there would be very little there because it's a very straightforward conversion.
Okay, thank you. Are there any dangers of using lambdas in conjunction with smart pointers?
I think I might need to understand more context about why that's asked. I mean, with a smart pointer, like unique pointer or shared pointer or something, if you're passing something in or capturing it, then it follows the normal semantics. I think the main danger that I've seen with lambdas, and really it applies to any functor, but it happens with lambdas a bit more, I think, because they're so easy to create and pass around, and you can end up with code that does this more easily because they're more easy to write, is that because they capture something, if you capture by reference, then you can often end up with something mutated, something changed, and you do need to be aware that can happen. And this is one of the benefits actually of seeing a Lambda inline, because you can see the code that it writes and you can see that it captures something, and so it's all very explicit on screen. But the same issues that occur anywhere where you need to be aware that data can be written or modified occur with Lambdas. In fact, actually a thread would be a good example, because I showed earlier a side with a Lambda providing the thread function. Now that function will be executed in another thread by definition. But if you use variable capture and you happen to do something that's thread unsafe, perhaps you capture something by reference and multiple threads are writing to it at the same time, or something like that, then that would obviously cause problems. And that's not really a problem that's inherent to lambdas themselves. It's just that they make writing little function objects so easy that you need to be aware of what can be captured and what scope or access they have. So I'm not certain I completely answered the question. I think I answered it with a different concern that is one that I'm more aware of. I hope that helps.
Great. This interesting question. Even if they're written in line, for example, inside std sort, I expect the readability of a lambda to change with the size of the code inside the lambda. Do you have a recommendation for such large lambdas?
Yeah, that's a good point. And the readability does change. I think the thing I want to contrast is where you have the body of a method, let's say off screen. Even if you just scroll up by a few lines and you see it because it was defined above where your code is, versus seeing it right there. But of course, if a lambda starts growing, then you're right. It might start through the complex logic that it might have. It might actually make the surrounding logic more confusing. And at that point, I think you have a few options. You could actually define your lambda out of line. So let's suppose you have a I know, a loop and you're doing something and then you're passing in a lambda and there's a whole bunch of other logic. Because a lambda is an object and can be defined somewhere, you could actually define it just above that, assign it to a variable, and then use it inside your logic. I mean, or you could move to some other technique. It's hard to have a recommendation for exactly when it would start becoming complex. I mean, even if you have, say, a 10-line long lambda, if it's just doing 10 statements one after the other, then I personally wouldn't find that very confusing. But if it had a lot of nested logic for those 10 lines, I probably would find it confusing. So I think it's really just a matter of the complexity and the point at which what's inside the lambda starts visually or mentally outweighing what's outside the lambda. So the question asks for a recommendation, and that is not a recommendation, sorry, but perhaps a guideline of my own thoughts there, just a matter of when it starts, when it starts overpowering or outweighing the location where it's used.
All right, thanks for that. Miguel wants to let you know, great presentation, and then he asks, can you elaborate on your thoughts regarding functors with more than one built-in function, i.e. with different function signatures? Trying to replicate this with lambdas would be fairly cumbersome, wouldn't it?
It would. I mean, a lambda is effectively just writing a single function. And by definition, it is a single function object. Whereas if you have a structure that has, and if I understand it correctly, it's describing two call operators, two operator brackets, but with different function signatures. So you pass in an object, but when the call operator is invoked, a different one will be invoked. Lambdas aren't really a good solution to that particular use case. And I think that is the case where you'd pass in a struct with a couple of different operator methods in instead.
Okay. Can you talk about when not to use a lambda? When you would want to avoid it?
Or to me, I think just when they get too complex. When they get too complex, you move them out somewhere, and if you start moving them out somewhere, maybe there's some better way to do things. The other thing that I often see is people trying to cram too much sort of logic and state into a lambda, overusing the variable capture. At some point, you might want to start abstracting out to other classes with other logic or different ways of holding state or something like that. I'm giving a slightly vague answer because I happen to be quite a fan of lambdas and I actually really like using them, but I view them as direct replacements for functors. And pretty much everywhere that I have used functors in C++, I would use a lambda today. So answering where not to do that is a little difficult actually. And really, I just think it's that any language feature can be used in a way that can be confusing or is perhaps not entirely appropriate. And lambdas are, I think, intended really to be, there's no limits on them, but they're sort of intended to be, not too large. They're meant to be these, nimble little objects that you create and pass around in line. And so if you have some other use case that is, larger or more heavy, then perhaps something else would be better.
So then, along those lines, is there any use case to write a functor these days?
I mean, these days, all the places that I would have used functors, I now use lambdas. But because a lambda is effectively a functor, when you write a lambda, you're effectively writing a functor. There might be things about variable capture where you prefer different ways of initializing or storing state. That could be a good reason to have a functor with a constructor that you pass things into the way you might more normally when creating an object. You might have something which has some very complex logic. So You might have your call operator, but it might do a lot of things, and you might want to split that up into multiple methods. And so if you have a functor, you could make those private methods. And then the actual operator call, operator bracket bracket, might itself be quite small, but it actually does a lot. And that would be a good use case for a functor object as well.
Awesome. Do lambdas work?
Sorry to interrupt, but
oh, go ahead, David.
Miguel actually had a good use case as well, where he spoke of having two call operators with different signatures, but sharing some kind of state. And that's something you can't do with lambdas. So that would be an excellent use case for a functor. Sorry, please go ahead.
Oh, no worries. Thanks for circling back to that. This question, do lambdas work well with ranges?
Absolutely. I mean, I wouldn't see why not. I think they would work very well. They're both good modern C++ features.
Great. When would you use the capture portion instead of passing as parameter? Is that only when passing by reference?
Capture is useful when you want to. I mean, there are a couple of cases where it's useful actually. One is just for state. So you have some common state for every time the lambda is invoked or every time it is called. So you would initialize that state via capture. Whereas when you call a method, the parameters that you call it with are probably different every time. And the other time is by reference does allow you to write back outside the lambda. And so variable capture is a neat way to achieve that. Obviously, lambda can return a value, but given it's a function, and the same way any function can have something by reference and change the value that is referenced, or any class can have a field that is a reference field. That capture allows you to achieve the same thing.
Thanks, David. Not so much a question, but a comment from another David on the call, and I'll follow it up with a question. David said, thanks for the webinar, and he wanted to share another usage of lambdas that he found really useful to initialize and keep correct a variable when it's not trivial to initialize. And then he shared an article from Herb Sutter. So maybe you could, David, if you can think of any other use cases that aren't injecting code into other code, unlike the diagram you showed, if you could speak to anything along those lines.
Well, that's a really good point, and thank you, other David, for passing that in. I want to go read that. It rings a bell, and I think I might have read it once, and I had forgotten. So I really appreciate that comment. Look, the example I gave about sort of injecting code, I think is because it's a sort of common problem, and then passing in a function object of any sort is a very C++-ish way to solve it. But you can use lambdas anywhere that you need a method, and they're very useful because as function objects they can be assigned to variables and passed around. But really, you don't even have to do that. You can directly invoke one if you want to. If I'm right about what that article is about, then I probably shouldn't speak to it without reading it, and it does sound very interesting. But I think it is sort of a hack to achieve something, if I'm correct. And I'm sure there are lots of other things like that as well that I just can't bring to mind, mostly because I tend to use them and I've been focusing just on the function as an object as a variable sort of case.
Yeah, Andre.
Sorry, go ahead.
Oh, I was just gonna say that Andre chimed in and said he also uses lambdas extensively to avoid code duplication inside functions.
Oh, that's also a good one. Well, yeah, I think anywhere that you might duplicate code, it makes sense to refactor that out into a function, and using a lambda seems great. That's an excellent example. Thank you, Andre.
All right, can you tell us what was new in Lambdas since C++11?
Not everything. And I should have refreshed myself before the webinar. The vast majority of what was, comprised lambdas was defined in C++11, but I know there have been tweaks since then. There have been tweaks to variable capture. There have been tweaks to, and of course you can use new syntax now to define the the result type. Yeah, I would have to go and look that up. There are some great articles out there that are very easy to find. There's a lot of material on lambdas online, and actually, of course, CPP reference is very clear in its documentation. It labels specific things with the language version they were introduced. So I'm sorry I can't give you a quick summary, but yeah, 95% of it is C++11. The other 5%, which is genuinely useful, is well described out there.
All right, thanks for that. Is it possible to debug a Lambda while it is in use, or how do you debug it?
Oh, sure. I mean, you can just step into it, trace into it, depending on the terminology of your debugger, because it's a function like anything else, and so when it's called, you can you can step in and run through its execution.
Okay, here's an interesting question issue you could speak to, maybe David. I find lambdas very useful. However, passing a capture by value gave me some issues because the capture is done once and changes of the value are not seen by the lambda. Can you speak to that?
Yeah, that's true, because when you're capturing by value, it is a kind of initialization, so it is done once, and then when you change it, it's only changed within the scope is probably not quite the right word, within the the storage context of the lambda itself. And so if you want it to be seen outside the lambda, then you really need to capture by reference. And then since you have a reference, you'll be writing to the the value that you have a reference to, which is outside the lambda. And to do that, you just use the reference symbol, the ampersand, in the the capture section. Sorry, I'm just getting silence now.
I'm sorry.
I'm
here. I'm sorry. I toggled the mute one too many times.
Oh, no worries. I was just worried about my internet connection.
Yeah. We do have a couple questions here about where the audience can revisit or rewatch these webinars. If you go to YouTube and search for Whole Tomato, you'll find our channel. You can subscribe to it or just browse the videos in the channel. You'll see as they are uploaded, these webinars are available for full replay. So we have one or two more questions here, a few more minutes. So last call for any questions. We have one here, David. Why should a lambda be mutable if it changes something that was captured by value? Is there something special about such lambdas?
About the lambda itself being mutable when it captures something by value. I'm not sure of anything special as such. I mean, I think it is ideal for state to be non-mutable in general. And if you really want something mutable, then I know, I suppose it depends on how you're using the lambda. I think in general, I would prefer to have that state stored externally. But if you think of a lambda as the equivalent of a functor, a struct written with its own state, then it can, of course, be completely valuable to mutate that state based on the method being called. Because really, it's just a method that you're calling, and it's reasonable for it to do something. Doing something can involve changing state. Although it would be odd if the results of that weren't reflected somewhere outside the lambda at some point. I hope I'm answering the question because I'm not completely convinced I actually understand the question fully. So apologies if that's an answer to a question that you didn't actually ask. By the way, there was a question earlier just a few minutes ago about what had changed since C++11, and I just saw in a chat that Chris, our lead dev, reminded me that move semantics was new in C++14 for lambdas as well. So that's a great point. Thanks, Chris.
Also point out that Andre has said post C++11 there are now generic and even full template lambdas, and that lambdas can now capture this by value.
Excellent. I should have researched this more and put an aside on what had changed since C++11. So thanks, everyone.
Yeah, thank you. That's excellent input. All right, well, that wraps it up for all the questions. David, thank you for the presentation, the great content, and to all of our audience, thank you all for your attention, your time, and for these questions. We appreciate it.
Well, thank you, everyone. I hope you found it interesting. Not too light an overview. I tried to make it selling the value rather than a huge in-depth look, but hope you found it valuable, and thanks for attending. Hope you've attended some of our other webinars or some of the others that we have coming up.
Exactly. We hope to see you all in the next one. Thanks, everyone.
Goodbye.
Bye.